the Syndicate, was on the move. It called for quick evasive action. This was a job for Barr. Our mission, to detect, track, and avoid the most dangerous power group in the world, the Atmospheric Storm Syndicate.
East 636, clear for immediate takeoff.
Wing flaps are set.
Okay, we're rolling.
Takeoff power.
Takeoff power.
Call out VR.
VR.
Gear up.
Gear up.
Max continuous.
Max continuous.
Flaps up.
Flaps up.
Climb checklist.
Gear lever. Lights out and off. Wing flaps. Up. Landing lights. Off. Altimeters. Reset here. Star switches. Off. Air conditioner pressurization. As required. Pressure and temperature.
May I have your attention, please? Would you kindly check that your seat belts are securely in? Our captain reports that we will be making some detours to avoid poor weather ahead. Thank you for your attention.
Turbulence, jolting, jarring, hazard to all pilots and passengers. This is the Menace, former public enemy #1 of commercial and general aviation, the Thunderstorm. Method of operation: turbulent, deceptive, dynamic, striking with lightning and hail. Leading character and most lethal member of the Atmospheric Storm Syndicate, containing more energy than many nuclear weapons. They loom awesome in power, ranging from 140 million horsepower for a benign thunderstorm to 50 billion horsepower in the king-size member. Until the science of meteorology and radar engineering teamed together in the early 1950s, relatively little was known of the basic dynamics of thunderstorm structure. Today, a full-scale attack on the problems of turbulence is underway on all fronts. Teamed together in this massive assault are the airlines, industry, government, and university laboratories. Some of the questions to be solved affect the continued safety of aviation. Are the mechanics of all thunderstorms the same? Does 10 years of turbojet operations reveal a need for new and more cautious techniques? Do hidden tornadic vortices lie in the flanking line of severe thunderstorms? If so, can airborne radar help identify their location? To date, however, there is no weapon to detect turbulence. But there is one tool to detect the sources of severe weather turbulence: radar. Developing this tool to a high degree of dependability for effective pilot use has been the major concern of the aviation community for over a decade. One of the most dramatic research programs on severe thunderstorms was conducted by ESSA, Environmental Science Services Administration, using a specially instrumented Air Force F-100 aircraft in high-altitude studies. This project has done exceptional work in defining the hazardous areas associated with high-altitude turbulence and hail strikes. Test programs with this aircraft have included penetrations of severe storms at speeds of approximately 0.66 Mach. One test with an F-106 aircraft made penetrations at airspeeds approaching Mach 2. This particular F-100 flight dramatically confirmed the danger of bullet-like hail strikes in and around storm cells. A good background of what radar can do and what it can't do on the ground and in the air can be of immense value to all pilots. Let's start on the ground. Universities have contributed immensely to the advancement of this tool for the pilot. Few universities have done more than the Radar Meteorological Laboratory at the University of Miami. Here, Professors Homer Heiser and Harry Sen teach and conduct research on various types of storm and abnormal weather radar propagation. Over 100 technical reports on severe weather findings are credited to the staff of the Radar Meteorological Laboratory. Bendix Avionics Operational Training Manager talked with Professor Sen about the emphasis the pilot should place on adjustment and interpretation of his airborne scope.
PPI scope. Well, first of all, we've made some pretty great strides in being able to build a relatively foolproof device for the pilot. However, you have to consider very carefully the fact that on the ground we have electronics engineers and technicians helping us to adjust this thing and keep it in tune. In the air, this is up to a pilot who doesn't have this kind of knowledge and who has to literally practice his art as he does his flying. The scope setup is reasonably critical on almost any radar, and the pilot, of course, has to be aware of this. He can fool himself as to how much or how little weather there is on the scope. And, of course, the probability is that he's losing more weather and not knowing it. It's far too easy to end up with a clean scope. The confidence level, of course, with any tool, or the confidence level of the pilot in his own ability to handle a given airplane, I'm sure, is as a result of his practice and hours with it. And unfortunately, I think in some cases radar has been a little oversold as possibly an oversimplified tool. It does require practice by the pilot, who is the operator, not only in setting it up, but in reading it and interpreting what he sees.
No radar, ground or airborne, sees turbulence. It sees, rather, areas of high moisture content. Some authorities feel the heavier rainfall areas are generally associated with greater turbulence. Searching and evaluating these weather environments where turbulence exists begins with a basic pilot knowledge of meteorology. Good flight planning always starts with a thorough weather briefing, locating frontal lines, low pressure systems, wind speeds, and temperature. Yet, even with the most thorough pre-flight briefings, the terminal weather picture can alter. conditions can deteriorate to a point where expert know-how and operation of airborne radar are demanded of the pilot. Some help, of course, is available from the FAA controllers. As public guardians of our nation's airways, FAA control centers are primarily concerned with air traffic movement. Unlimited weather surveillance for all pilots is not possible at the present time. To the pilot asking for a weather vector, this special emphasis should be kept in mind. Traffic control radar, though not specifically designed to map weather, can provide some weather information and sees a broader area than the pilot's scope display. However, as most ground radars have no contour function, consequently, they may see less detail than airborne radar. Thus, some controllers see only the overall precipitation area, not the black holes of rain that airborne radar sees in contour mode. Traffic control radar operates in two modes, CP and LP. LP mode displays all normal transmissions without discriminating between aircraft and weather targets.
Flight level 18,000, estimating us for 10911, Nancy.
As the ATC makes the shift from LP to CP, we see the weather returns diminish. In CP mode, a technique is used whereby radar waves are shaped as they leave the antenna so that echoes from precipitation will be de-emphasized. Consequently, most rain clutter is erased so that the controller can see the traffic. CP is used when weather clutter begins to interfere with the traffic picture. Under certain conditions, it is possible for the pilot to request the controller to switch from CP to LP. But the controller can't do so if he cannot see his traffic on LP. Unless the pilot knows the controller is on LP mode, he and his radar alone are the prime determinants in detecting adverse weather, evaluating its intensity, and starting evasive maneuvers early. The earlier, the better. Starting on the ground, in the cockpit. The cockpit checkout is the starting point for full and effective use of airborne radar. In terminal areas, setup procedures begin by observing clearances around traffic and structures in the area. On the control panel, set the function switch to standby. Turn the gain fully clockwise to fixed or automatic. Tilt the antenna to 10 degrees up. On the PPI indicator, adjust the erase rate fully clockwise. Set the trace adjust fully counterclockwise. Turn range to 180-mile position. Rotate filter as required. Advance function switch to test mode, which disables the transmitter. Within approximately 20 seconds, the standard test pattern will appear by turning the trace adjust in a clockwise direction. From the apex, 0 miles, to approximately the first range mark, no noise or video should be displayed. Somewhere between the first range mark and the second mark, a definite coarse grain band should be visible. Rotate the erase rate until the video display is retained for a maximum of 270 degrees. To avoid smearing during aircraft maneuvers, no portion of the display should be retained for a longer period. Between 60 miles and approximately 110 miles and above 150 miles, a light sprinkling of background noise should be visible when the trace adjust is properly set. This assures optimum detectability of weak targets. In adjusting the erase rate control, take care not to adjust too far counterclockwise. Over-adjustment of the erase rate will build up brightness in some areas of the display that may blot out the normal responses. The radar is now adjusted for suitable display when set to normal or contour. Setup procedure for the 300-mile scope is identical. However, it produces a distinctively different test pattern. Prior to takeoff, switch from the test position to the desired operating position. 3 to 4 minutes is required from first turning the function switch from the off position before the normal function can be used. If in the normal or contour mode, tilt the antenna to a position between 0 and 5 degrees up. This will bring up weather targets within the vertical scan range of the antenna during climb-out. Here the pilot notes 2 storm cells, 60 degrees to the right. Do not change gain from auto. Adjust trace and erase for optimum display. The following airborne sequence was filmed aboard an Eastern Airlines 727 aircraft off the coast of southern and western Florida during the late thunderstorm season of 1967. The new 300-mile PPI scope was used in conjunction with other components of the RDR-1E. This longer range PPI is a component of the RDR-1F system. This sequence was taken on the 150-mile range right after takeoff from Miami and heading south over the Atlantic. Our altitude, 15,000 feet. Antenna setting 1 degree down on automatic gain control. Small to medium air mass storms are scattered across the scope and even clearly apparent beyond the 150-mile range ring. In all stages of flight, especially the initial phase, it is imperative for the pilot to keep this big picture in view. Adjust system for optimum long-range weather detection and plan detours early. This practice will allow time for the pilot to contact ATC to arrange necessary clearances to avoid weather targets. Perhaps the most important control determining both the total coverage and quality of the weather picture is antenna tilt control. Both extremes, too high and too low, exact a serious penalty when the pilot attempts to evaluate the entire weather picture. This sequence, taken on the 150-mile range, illustrates the pilot's attempt to determine the optimum antenna setting for the route he was flying. The antenna was tilted from 10 degrees up to a minus 10 degrees. Each sweep is equivalent to 1 degree of tilt. Note the significant changes in the weather pattern, cell size, and contour detail which occur with each sweep. 10 degrees up. 9. 8. 7. 6. Echoes are showing close to the aircraft. 5. Echoes appear up to 60 to 80 miles. 4. Echoes out to 90 miles. 3. Good contoured echoes out to 110 miles. 2. An almost ideal display of weather out to 150 miles. This setting was considered as optimum for the conditions of moderate to heavy precipitation along this flight segment. Here, the antenna beam is slicing through the entire cell areas, consequently displaying the full cell diameters with excellent detail. In addition, note the light sprinkling of land return on the left, which was considered desirable because it confirms that the beam is not over-scanning or slicing the cloud tops, but is seeing the entire diameter of the cells. A bright altitude circle appears around the apex as the sequence ends in extreme down tilt. Switching to 50-mile range permits the pilot to see excellent contour of storm cell on 30-degree relative azimuth at 40 to 50 miles. Note how the intervening precipitation surrounding the entire 10-mile radius in front of the aircraft does not hinder the pilot's view of this strong echo to the right of the scope. The character of a thunderstorm target can change dynamically in a very short duration. Close monitoring of the scope is necessary when detouring cells. A wise operational procedure is to give all major storms of this character a 15 to 20 mile clearance from the edge of the echo. Is the pilot seeing all the weather he should see on his radar? The answer to this persistent question often depends on how sensitive adjustments are made to antenna setting, erase rate, trace adjust, and gain controls. In systems having automatic gain control, this should always be in the automatic mode when mapping weather. The following footage shows a series of examples where significant weather targets are lost or distorted due to incorrect control settings. In the first sequence, the erase rate, which controls the duration of the video display on the scope, was intentionally mismanaged by the captain to show the obvious effects. Note how the otherwise excellent cell contouring on the right is lost in the resulting blooming on the scope. Several seconds later, with the same storm cell now on the 50-degree azimuth heading, the trace adjust, which controls the intensity of the video display, is also mismanaged intentionally by the pilot. First, too heavy. Then, too light. Here again, we note the weather 40 miles ahead and to the left of the aircraft is lost, while a drop in definition affects the contour of the storm cell. As the aircraft flies closer, exceptionally detailed contouring is revealed, with gain set on full automatic. Such fine detail may be attributed to a sensitive handling of the antenna control. This sequence proved an excellent example of the marginal situation which can develop quickly when the pilot doesn't keep the long-range picture in view so as to plan detours early. In this situation, it is difficult for the pilot to allow a clearance of 15 miles or one range ring between each of the targets. Within a matter of minutes, as the pilot approaches the decision point, the cell on the right was observed to split. Here the pilot elected to go between the targets, giving a full berth to the more severe cell on the right. Here on the 50-mile range, very heavy rain cells are shown in front of the aircraft at 20 miles, with very sharp contours on the leading edges. Gain setting is on auto. At top right, a common area of ambiguity can be observed. A +1 degree up tilt of the antenna at this altitude, 14,000 feet, causes us to paint Cape Sable on the lower tip of Florida. Overlaying this ground return are a number of strong storm cells which show up as black holes, but only when the contour function is on. However, this same area is characterized by some large lake areas which also show as black holes in the return. Again, a small variation of antenna tilt would permit the pilot to distinguish the actual weather cells. Here we see on the 150-mile range, 25-mile range marks, the same weather plus ground situation that was previously shown. Now the outline of the southern tip of Florida and the west coast are clearly defined. This sequence is significant for two reasons. First, on the longer ranges, the small yet severe cells at the tip of Florida become almost indistinguishable with the ground clutter surrounding them. Had the pilot not used the contour function, the radar would not alert him to the presence of such cells. The second feature in this sequence is the presence of two apparent dark notches seemingly radiating out from the apex of the scope, and appearing on the back side of the ground returns. Heavy rainfall rates can cause some attenuation of radar energy. However, the rainfall rates severe enough to cause appreciable attenuation at X-band frequencies almost invariably occur in shafts of quite restricted diameters. The ground clutter is due to the fact that the lower edge of the radiated beam is just grazing the Earth in this area. This results in a highly marginal signal return. Hence, any appreciable attenuation in the intervening storm shafts tend to cast a shadow on this ground clutter. In a situation such as this, it is sometimes noted that weather targets, which are good strong targets at this range, will show up in this shadow, whereas they were lost in the ground clutter otherwise. Here, as in the previous sequence, a degree or two additional up tilt would have eliminated most of the ground returns and emphasized the weather targets. Using the 50-mile range, the pilot flies around the cells which were embedded in ground replies, so his radar could pick up the entire weather pattern. Here are the same heavy precip cells at half gain. While the drop-in gain has succeeded in removing the ground return of the coastline, the pilot now has a diminished and deceptive image of the size and intensity of the storm cells. Consequently, this technique should be avoided. Resisting the temptation to use gain control rather than antenna adjustments to remove ground clutter cannot be overemphasized. Changes as small as 1/4 degree may make a surprising difference in the display. In this sequence on the 50-mile range, 2-degree antenna up tilt and contour on, we see a strong finger of precipitation, indicating an area of turbulence at about 35 degrees extending towards the aircraft. The black holes at the top of the frame, around 45 miles from the aircraft, are identified as lakes and ground return along the Florida shoreline. On the 50-mile range, our radar is switched on normal function. The scope shows a large mass of precip mixed with ground return in an ambiguous display. Plus 1-degree antenna up tilt is used. By turning to iso-echo contour, we immediately see a large number of storm cells buried in the precip over the coast. No storm cells are over the Gulf in this area. Most pilots hear such terms as contour and IEC. In radar terminology, this means iso-echo contour. When the intensity of the return signal increases beyond a preset level, which is that caused by an instantaneous rainfall rate equivalent to approximately 1/2 inch per hour, the video return on the PPI scope is inverted, becomes black. This produces the series of black holes, which represent the cores in the storm cell. The rainfall rate, therefore, is greatest in these black centers. In this unusual sequence, taken on the 50-mile range with 2-degree up tilt, the radar beam displays excellent contour definition on the massive cell ahead and to the right of the aircraft. These cells were classified as moderate to heavy precip by both meteorologists aboard the aircraft, Paul Kadlik of Eastern Airlines and Professor Harry Sen of the University of Miami. Analysis of the long finger-like projections at the 30 to 35-mile range proved more interesting. Post-flight investigation at the Radar Meteorological Lab at the University of Miami indicated that our airborne radar was displaying the ice crystal and supercooled water in the cirrus blow-off from the small contoured cells on the tip extremities. The aircraft was on an easterly heading across the southern tip of Florida at an altitude of 14,000 feet. Upper winds at the cirrus level were carrying the blow-off, which was above 25,000 feet towards the east at about 30 knots. This type of scope image, however, is generally best displayed only when the aircraft is at an intermediate altitude where the antenna beam is radiating up through the long shaft of the wet anvils. The same type of wet anvil formation shown on the scope display was shot from the aircraft window several minutes later and is representative of the anvil tops in the region. In this sequence, the radar is switched to normal. Note that without contouring, the pilot loses all indication of cores within the severe cell to the right and cannot identify the cell which is producing the blow-off. In addition to its principal function of weather avoidance, the RDR-1E also provides the pilot with valuable terrain mapping data. Here, an excellent ground map of the Miami area on the 150-mile range features a finely detailed display of Biscayne Bay at 45 miles dead ahead of the aircraft heading. On the 50-mile range, the detail of the bay area is almost fine enough to see the causeways connecting the beach to the mainland. For optimum ground display when mapping, the gain control may be adjusted in the counterclockwise direction. The basic antenna tilt system positions the beam with respect to the mechanical center line of the airframe. The stabilization system of the 1E transfers this airframe reference to a gravity, vertical gyro reference. The combined function maintains a select beam tilt, which is independent of moderate pitch and roll displacements. The stabilization system of the 1E radar is based on a fixed line of sight. The beam tilt is continuously controlled as the antenna rotates in azimuth. This compensates for pitch and roll displacement of the airframe. Displacement data is obtained from the vertical gyro reference system. In the following sequence, with the antenna set on 0 degrees, the aircraft was rolled in 5-degree increments to the left and right, starting with 25 degrees and terminating at 45 degrees. A good roll reference point is the double core cell dead ahead of the aircraft. Note how all targets remain reasonably stable and sharp for rolls of plus and minus 25 degrees, which are the stabilization limits for this particular antenna. Only when the pilot exceeds the antenna stabilization limits of his particular system in pitch and roll parameters does the radar lose some of the weather targets on the sides of his display. During the summer of 1966, the FAA, in conjunction with the National Severe Storms Laboratories, conducted a series of tests using a modified RDR-1E system with a 300 nautical mile range. One interesting result is shown in the following series of sequential photographs taken at 30,000 feet. This particular storm sequence contains 2 lines of storm cells, one dead ahead, the other to the right. Both are significant in that they appear much the same in shape and format at all ranges from 100 miles out into the closest approach. The storm at the left appears to be a mature storm line which contours stronger at 100 miles than at close range, indicating possibly some decay in the 6-minute interval between first and last shots. At a 100-mile range, the storm system on the right appears to be only of moderate interest. Yet, in a matter of minutes, and while still at considerable range from the aircraft, it flares in intensity. The greatest turbulence in this cell, of course, will probably be found where contour is most prominent and where the hook is starting to form at about 70 miles. Some authorities feel that such a hook is often indicative of hail. Since the apparent growth here is not primarily attributable to the range change, we are witnessing a remarkable example of storm dynamics. In this case, the pilot was able to monitor the storm's growth accurately through the advantages of 80-mile normalized display. The pilot reported breaking off the test at this point and executing a 180-degree turn. At the conclusion of the weather flight program, additional operational aspects were reviewed with Paul Kadlick of Eastern Airlines. He emphasizes the critical importance of maintaining proper gain settings.
This is why we want to also maintain a more or less fixed gain position on the gain control knob. If the airplane does not have fixed gain, we would encourage the pilot, of course, to adjust his radar initially to get his best pattern and then leave the gain setting alone, because if he should adjust it or change it, he would very possibly miss some of the rapid development of contours and the edge of the sail, which we're looking for here. And if he did not return the gain to the exact position he had before, he would very possibly miss the development of other sails ahead of the airplane.
Today, airborne radar is one of the most essential items on the pre-flight checklist.